Welcome to The Explainer. Today, we're diving deep into the cosmos to get a handle on the universe's most fundamental, most powerful force. We are, of course, talking about gravitation. It's like this invisible thread that connects literally everything in the cosmos. It's the silent director of this huge celestial ballet. And, it's the very reason our feet are planted firmly on the ground right now. So, let's kick off our journey right here, exploring how this fundamental force is woven into the very fabric of our existence, from the simplest little things we do every day to the absolute grandest events happening out there in the cosmos. I mean, think about it. From a falling apple, the classic example, to the incredible dance of the planets, gravitation is the unseen choreographer of the entire universe. It's the reason the moon orbits us so faithfully, which in turn creates the ebb and flow of our oceans. It's what keeps our whole solar system in this delicate, predictable harmony. And it's what makes sure our satellites don't just, fly off into deep space. Okay, so how do we actually describe this universal force? How do we put a number on it? Well, the answer comes from a single, totally revolutionary idea from none other than Sir Isaac Newton. This is really a cornerstone of physics. It explains that everything with mass pulls on everything else with mass. So you have a gravitational pull, the desk in front of you has one, and a planet like Jupiter has a massive one. The more stuff an object has, and the closer you are to it, the stronger that pull gets. And there it is, the master equation itself. Isn't that something? It's just amazing to think that the entire dance of the cosmos, the pull of the tides, it can all be described by this one really elegant relationship. So let's break down what each part of this actually means. Okay, so as you can see, the force, F, it all depends on the masses of the two objects, that's m1 and m2, and the distance between them, which is r. But what about that g? That is the universal gravitational constant. You can think of it as a kind of cosmic conversion factor. It's the special number that makes all the units work out perfectly, making sure the equation gives us the right answer whether we're talking about the pull between two bowling balls or two supermassive black holes. All right. Let's bring this huge, grand concept back down to Earth and see how it all plays out right here, in our own gravitational playground. Now, there's a subtle but pretty important distinction to make here. Gravitation is the big, universal principle. Gravity, on the other hand, is usually what we call it when we're talking about Earth's specific pull on us. So all gravitation is a form of gravitation, but not all gravitation is what we call Earth's gravity. It's kind of just a local nickname for a universal phenomenon. We all learn in school that the acceleration due to gravity, we call it little g, is this constant number, 9.8 meters per second squared. But is that really true everywhere on the planet? You might think so, but it turns out the pull you feel from our planet isn't exactly the same everywhere you go. This actually means your weight can change depending on where you are, even though the differences are super tiny. If you're on top of a mountain, you're farther from Earth's center, so gravity is a little bit weaker. And since the Earth is kind of squashed, the poles are closer to the center than the equator is, making gravity a tiny fraction of a percent stronger there. And get this, the planet's spin at the equator actually pushes you outwards, counteracting gravity and making you infinitesimally lighter. So, this all leads to a really thrilling question. If Earth is always pulling on us, what would it take to actually leave forever? How fast would you have to be going to just completely escape its grasp? This speed is called escape velocity. It's the point where you're no longer in orbit. You are on a one-way trip out into the solar system. Imagine throwing a ball so incredibly hard that it just never comes back down. That's what we're talking about here. It's the moment an object's kinetic energy, its energy of motion, finally overcomes its gravitational potential energy. For our planet Earth, that magic number is a staggering 11.2 kilometers per second. That's over 40,000 kilometers an hour. If you're going any slower, you'll eventually fall back down or get stuck in orbit. But if you're going any faster, well, you're headed for the stars. And the way we calculate this speed comes directly from the principles we've been talking about. But here's the part that always blows my mind. The escape velocity depends on the mass and the radius of the planet you're leaving, but it has nothing to do with the mass of the object that's trying to escape. A tiny feather and a giant spaceship need to reach the exact same speed to break free from Earth's pull. How wild is that? All right, let's put our newfound understanding to the test. Let's try and tackle a classic cosmic puzzle. Because, it's one thing to know the formulas, but it's another thing entirely to actually apply them. Okay, this is a fantastic question. It really forces us to think about how gravity behaves inside a planet, not just outside of it. Now, your first instinct might be to think, well, I'm getting closer to the center of all that mass, so gravity must get stronger, right? Let's see what the physics actually says. The solution here is so fascinating. As you go down into the Earth, something really weird happens. The shell of rock and iron that's above your head actually starts pulling you upwards, and that partially cancels out the pull from all the mass that's still below you. The math tells us that the net effect is a straight, linear decrease in gravity as you get closer to the center. So if you're halfway to the core, the gravitational pull is exactly half of what it is on the surface. Your weight would drop from 500 newtons all the way down to 250 newtons. So what this little puzzle shows us is that understanding Newton's law isn't just some academic exercise. It actually gives us this incredibly powerful tool to predict and calculate how the cosmos works. This knowledge is not just for passing exams. It's our key to unlocking and navigating the entire universe. I mean, every single time we send a probe to Mars or place a communications satellite in just the right orbit, we are using these exact principles. It's literally the mathematical language of the heavens. And that brings us to our final thought. Newton gave us this incredible map of the cosmos, a map that works astonishingly well for pretty much everything we do. But about a century ago, a guy named Einstein came along and basically said the map itself needed to be completely redrawn. He suggested that planets aren't being pulled by the sun, but are instead just following straight lines through a universe that has been warped and curved by the sun's immense mass. But that's a story for another explainer.